So what are you guys?
We're part of the Smartwood family.
Hey guys, we had an interesting question come in, and it actually has a surprisingly simple answer. So let's take a look at this. So let's say you have some number of urns, okay? And let's say you can tell the urns apart, and you've got urns, say, number 1, 2, up to, say, alpha. Okay, let's do that. All right, and let's say you have a certain number of balls. Well, actually, let's say it this way. You have indistinguishable balls, and you can place them in there. And I want to know how many ways you can do this if the number of balls has to be less than or equal to k. So k is a fixed number, and the number of balls you drop in has to be less than or equal to k. And we're going to have one more condition, and that condition is we need at least one ball in each container. Okay, so at least one. Okay, so obviously that means that k is the total number that we're looking at. The number of balls, let's call it n, that we could drop in. That's going to be at least less than or equal to alpha, because you need at least one ball per container. Okay, so the question really is, how many ways can this be done? Okay, all right. So, by the way, if you want to formulate this a different way, it's also a way of thinking like if you have this plus, similar to our other videos, x alpha, like that, right? Where the numbers here are basically the buckets, and the number of balls you drop in there determines the number we're going to assign to this. And all the numbers we're going to assign, each of these guys, has to be what? Greater than or equal to 1, because we're going to put at least one ball in each bucket, right? And we're going to have them sum to any number that's less than or equal to k. Okay? So those are actually equivalent formulations of the same problem. So if you saw other videos, then this kind of builds on that. Okay? Okay, so I want to make sure we're absolutely clear on this. The understanding is this. So you have fixed alpha urns. No choice about that. Okay? So alpha is a fixed number. Each container must have at least one ball in it. So the minimum number of balls we can have in this game is alpha. And n is going to represent the number of balls. Okay? Of course, if you have to put one in each, the smallest number this could be is alpha. And k, which is a fixed number, that's going to be the max number of balls. Okay. So what we want to do is we want to compute how many ways can we do this? How many ranges can we get? We have exactly alpha containers. We put at least one ball in each of them. And you can put down as many balls as you want, as long as there's one in each and you don't pass k. Okay? How many different ways can we do this? Well, one way is, let's just do a general case. The easiest case, I think, is if there are alpha balls. So let's set n equal to alpha. So this is the number of balls. This is the number of containers. So this is really the case where there's just one ball in each container. Okay. You already know the answer to that, but I want to work on how we can think about this problem. Okay? So first let's lay down, say, all the alpha balls. So there's 1 up to ball n, which in this case happens to be alpha. Okay. Now, we've seen this idea before. If I want to delineate 3 different containers, and I want to place balls in between them like this, one way to encode this is you put down the balls, like that. There's 5 of them, right? I just made up the number 5, just to make a point. And in here, we have 3 containers. But to identify the 3 containers, we just need to know where one ends and the other begins. So you can convey that information with 2 dividers. Does everybody see that? So if I wrote something like this, this is similar to, but not exactly the same as what we did in the previous video. Because in the previous video, we allowed there to be no balls in a given container. This time, every container has at least one ball. Okay? It actually makes the problem slightly easier. But do you guys agree if I wrote this down, you would understand that means container 1, container 2, container 3. Okay? Do you also agree if I wrote this down? That would mean container 1, container 2, container 3. Okay? Now, in the old way we did it, you could also theoretically write this down. And that would mean container 1 has 2 guys, container 2 has nothing, and container 3 has 3. Okay? But in this setup, this is not going to be allowed. Okay? The reason why is every container must have at least one ball in it. But regardless of how you do it, everybody agrees that you can encode this information, right, the setup, by telling me where you put the dividers. The only rule is you can't have the dividers next to each other. Okay, so maybe one way to do it is this, a slick way, is that we put down our n guys, and then we think, how many guys, so could we put a divider here? No, because if we did that, that would indicate a divider were empty. Could we put a divider here? That's the right edge of one urn and the left edge of another. No, can't do that, because that urn would be empty. So this part here is not legal, this part here is not legal, but any of the spots in between are legal. And you can't have 2 dividers next to each other, right? Okay, so why don't we do this? Why don't we just lay out all the n guys, and then just imagine spots like this between them. Okay? And then what we want to do is pick where the dividers go. Only one divider, though, per little bump here. Right? Because if you put two dividers here, you have that problem, which we don't want. So all we need to do is count the number of spaces we have here, right? And then from them, pick the positions of the dividers. That way, you don't have one here, you don't have one here, and since we're picking from these, you can pick this and this, that would indicate that, but you're not allowed to pick this twice, okay? Okay, so basically you're picking without replacement. You know it's going to take us toward combinations, okay? All right, so let's see how that works. Well, if you put one here, that'd be 1, 2, 3, corresponding all the way up to n. Okay, so there are n spots here counting the starting caret here, okay? But I'm going to remove that. So I think here there is n minus 1, okay? There are n minus 1 guys here, okay? All right, and of these spots, right, we would like to pick out, initially I would think alpha of them to be the dividers. But remember, to delineate 3 containers, you just need 2 dividers. To delineate 4 containers, you just need 3 dividers. So it's not really alpha, but it's alpha minus 1. Is everybody about that? Okay. All right, I did that a little bit quickly because I want to focus on some other things, but make sure that you're comfortable with this. If not, write in the comments and I'll do a video on it. But you want to be very comfortable that this is the way of figuring this out, okay? And in fact, this works in general, right? I didn't specify what n is. Now, I wanted to start with the case n is equal to alpha. But my bad, as I was just doing this on the fly, we actually did it in general. So our argument applies in general, okay? So whether n is equal to alpha or alpha plus 1 or alpha plus 2, whatever it is, this argument still works. So how do we figure out all the possibilities? Well, like we said, you could start with n equal to alpha. Then this thing becomes alpha minus 1, choose alpha minus 1. That is 1, but you know that. There's only one way to place one ball in each urn, okay? But then what are some more possibilities? Instead of putting down alpha balls, right, because this is n right here, you could put down alpha plus 1. So it'd be alpha plus 1 minus 1, which is really alpha, right? Choose alpha minus 1. Does everybody see that? And what if you put in one more ball? Then the argument would become alpha plus 2 minus 1, alpha minus 1. Okay? Dot, 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 all the way up. So what's the max number? The biggest number that n could be is k. So then you would have k minus 1. Choose alpha minus 1. Okay. Now the person that originally sent this in presented exactly this problem. I think it was phrased slightly differently, maybe in terms of the x1 plus x2 plus x alpha, but it's the same problem. And they said that their professor said the answer looks like this, and that is totally right. So if that's what your prof wants you to do, being mellow, that is totally the right idea, and that gets you the answer. It just turns out this is very nice because it has a compact form, okay? So my claim is that this number here that we've added up, by the way, if you look at this, it's basically alpha minus 1, if you just clean this up, to alpha plus 1, all the way up to k minus 1, right? So you start at alpha minus 1, you go all the way up to k minus 1. Okay, this sum, if I'm not mistaken, is actually going to be just k, choose alpha. It's very, very pretty, okay? Now, if you know this combinatoric identity, you can just use it. But I think it's really useful to see where this might come from, okay? Because this identity is kind of a neat identity. So it's basically like if you start at some point, right? And then you keep the bottom fixed and you work your way all the way up and you end at some point, that's going to be equivalent to k choose alpha. I kid you not, okay? So again, this is a very common identity. You might already know it, but the point of this video is to see kind of like where this comes from, or at least one way of picturing it, okay? And how it directly relates to what we just did. All right, by the way, a compact way of writing the same thing would be you're just going to take whatever this is. It's n minus 1, alpha minus 1, because alpha is not allowed to change. And you go from n equal to alpha all the way up to k. Okay. I think something like this is the answer the professor actually advocated, which is just this, the same thing. Okay. All right. So let's talk about this idea. All right. Remember what we just did? Remember how we argued it, right? You put down alpha balls, then alpha plus 1, then alpha plus 2, all the way up to k. Okay? So you have sort of alpha balls up to k balls. Okay. All right. And the m was just basically a placekeeper. The m was saying, okay, right now we're talking about alpha, and now alpha plus 1 all the way up. And remember the associated coefficients look like this. Alpha minus 1, choose alpha minus 1. Then say alpha, choose alpha minus 1. And then all the way up to k minus 1, choose alpha minus 1. Okay? And this, again, to understand this, you have to go back to our argument where we talked about placing balls in urns. Okay? Now, I want to kind of think of this a different way. Claim is this is equal to k choose alpha. Right? But what I want to do is visualize what k choose alpha means. K choose alpha. So we're going to do that. So that's basically you have a group of k guys, out there, and you're going to pick from them alpha. Okay? So you're going to pick out alpha. All right. So what are the things we're assuming when we're doing this? So number one, we're assuming that these k guys are distinguishable. So unlike the setup here, when you do k choose alpha, one way to visualize it is that literally you have k balls that are, for example, numbered. So you can tell them apart. 1, 2, 3, 4, 5, whatever, up to k. So these are k distinguishable balls, and you're going to choose alpha of them. Okay? All right. So in effect, what it is really like taking the numbers 1 up to k and picking out alpha of these guys. If you want to make it concrete, make alpha a number like 5. Okay? Like literally pick the numbers, for example, 1 to 10. And you're going to have alpha equal to 5. And you want to pick out 5 of them. Okay? That's what's going on. Okay. So since these guys are distinguishable, and we're talking about finite guys, of course, I'm going to sit there and I'm literally going to order them. Because we've got a natural ordering, right? 1 is before 2, 2 is before 9, 9 is before 10, blah, blah, blah. Okay? There's a natural ordering there. Let's take advantage of it. So I'm going to basically look at this, and we can make it concrete, and then we'll transfer it to the general case. Okay? So in this case, k is equal to 10, and alpha is going to be 5. And what I want to do is, if you pick out 5 guys, so here are 5 guys. Okay? We're going to pick them out. One way to do is grab your group of numbers. We don't care what order you pick them in. We just grab the numbers. But now I'm going to take advantage of this ordering. We're going to line them up from smallest to biggest. Okay? So one way of understanding or counting these guys is to look at the smallest guy. Does everybody see that? So you have all these possibilities, all these groups of, in this case, 5. They're all out there regardless, right? But you can always look at them and go, who's the smallest guy in each? And you can arrange them, group them, so that all the guys that say 1 is the smallest guy. You pull them over, classify them. Then let's go all the groups of 5 where 2 is the smallest guy. And you can pull them over. And that's effectively what we're going to do. So I'm going to do that. So imagine we have this set up here. And we have 10 guys. We're going to pick out 5 of them. And let's say in this particular set here, the smallest guy is, say, 1. Then all those possibilities, right? They might overlap or whatever. You kind of arrange them in sets where 1 is the smallest guy, 2 is the smallest guy, etc. Okay? I'm going to do this kind of succinctly. Who is the biggest, smallest guy, if that makes sense? You need to pick out 5 guys, right? Could 5 be the smallest guy in the set? Could 6 be the smallest guy in the set? Well, if 6 is the smallest guy in the set, then you need 7, 8, 9, 10. Looks like it's possible. Could 7 be the smallest guy in the set? No, because then you have 8, 9, 10. There's nobody to take that final spot, right? Okay, and remember, you don't have to draw them in order, but whatever group we get, we can put in order. And we're arranging them by the smallest guy in each set. So none of these guys could be, say, smaller than 7, because we designated him as the smallest guy. Okay, so by this argument, we said the biggest, smallest guy, if that makes sense, is going to be 6. So we can choose this guy to be 6, and then these guys have to be 7, 8, 9, and 10. So there's clearly only one set you can get where 6 is the smallest guy. Okay, I'll try to be systematic about this. So that's case 1. Case 2. How many groups of 5 can you pick out where 6 is not the smallest guy, 5 is the smallest guy? Okay, all right. So I kind of want to think of this. Well, 5 is the smallest guy. So how many guys are out there? Well, there's 10 guys, right? And of those 10, 10 minus 5 is 5. There are 5 guys that are bigger than 5. Namely, 6, 7, 8, 9, and 10. Okay, so there are 5 guys bigger than 5. Okay. Of the 5 guys bigger than 5, how many do you want to pull out? Well, you want to pull out 4. Okay. All right. Maybe there's a pattern here, but that takes care of everything, right? Because if you look at the 5 numbers that are left, right, and you need to fill these 4 slots, it's really going to be 5, choose 4. But if you go down here, if 4 is the biggest guy, then again, how many are left? Well, then you have 5, 6, 7, 8, 9, 10, right? And that looks like 6 slots. So of the 6 here, you want to choose out, again, 4. Now you can kind of see where we're going with this, right? The number of ways of doing this is 6, choose 4. The number of ways of doing this we just did was 5, choose 4. And if you think about it, there are 4 guys here. We had to use all 4. This is 4, choose 4. Okay? So the total number of possibilities is going to be 4, choose 4, plus 5, choose 4, plus 6, choose 4, right? All the way up. And each time it's going to be like 7, choose 4, 8, choose 4. Where are we going to end? Well, the smallest guy would be 1, right? And when you choose 1 as the smallest guy, all right, how many guys are left over? Were there 9 other guys? And if there's 9 other guys, right, that are out there, we're still going to choose 4. So this is an important point here. Does everybody believe that? Looking at this, how many ways can you choose from 10 guys, 5 of them? Well, you can add them up in cases. There's a case where 6 is the smallest guy. There's a case where 5 is the smallest guy, 4, all the way up to the case where 1 is the smallest guy. And if we wrote that out, we're going to get 10 choose 5 is equal to 4 choose 4 plus 5 choose 4 plus ... 9 choose 4. Okay? So what we're saying is you fix that bottom, the top starts at the same, you make these guys bigger, and then you end at, say, 9 choose 4. But this whole sum is going to be 1 bigger on bottom and 1 bigger on top. That's exactly this identity we're going for. So we see that? We fix this bottom. So this is this guy. We move from 4 all the way up to 9. We move from this guy all the way up to k minus 1. Okay, so this is k minus 1. What does this sum to? Well, this sums to 1 bigger than 4, that would be alpha, and 1 bigger than k minus 1, which would be k. And that is it. Okay? That's the heart of the idea. Okay, so now let's just go ahead and formalize it slightly. All right, so same thing, exactly the same idea, but now I want to do it in general. And we want to work on this guy. So we're going to pick the smallest guy here. Now with any number of slots, right? We know that how many positions do we need to fill? Well, there are alpha position guys we need to pick out. So this guy is fixed. So that means here the number of slots is alpha minus 1. So we're going to choose from here. Alpha minus 1. Okay. Alpha minus 1 numbers from what? Well, let's designate this guy. Let's call this guy, say, n. Okay? If this guy is n, how many numbers sit here? From here all the way up. Well, if you think about it, if there are k guys all together, and this guy is n, how many numbers are bigger than n going from n up to k? That's going to be k minus n. Right? An example of this is this here. So if, say, n is 6, right? And then k is 10. Okay, how many bit numbers are bigger than 6 going from bigger than 6 up to 10, or just bigger than 6 up to 10? That's going to be 7, 8, 9, 10. So it's the difference here. So it really is 4, right? Which is k minus n. So the k minus n guys we're going to place down here. Okay. So I guess that means for the case, for any general n, what you're going to do is you're going to pick a minus 1 guys to pick out from how many possible guys? K minus n. Okay? No big deal. Now the question is, that was a generic case, right? How do we do this thing where we're summing from the lowest up to the highest? Well, okay. Well, it turns out that if you're picking out alpha minus 1 guys, you have to have this guy be at least, so k minus n, right, is at least alpha minus 1, right? Otherwise, you don't have enough guys to choose from, right? So let's say k, I'm going to bring n over. You can also see it visually. I prefer to see it visually, but since we've done the hard work here, might also just do the algebra to help us. So this is k minus alpha plus 1 is greater than or equal to n. I just rearranged. But visually, you saw exactly what we were doing. We just need to figure out, I mean, we already know it's k minus n. We just want to get a label for n, and we want to do it in terms of everyone else, and you can solve that because you know that the smallest this value can be must be alpha minus 1. Okay. So the restriction is, in order for you to have enough guys here, n has to be basically smaller than this. So the biggest that n could possibly be is k minus alpha plus 1. And the smallest n could possibly be is definitely 1, right? Because we have the numbers from 1 to 10. The smallest value n could be is 1. Okay, so you're going to look at this guy, this sum, and it's going to be reversed, but that's okay. You're going to look at this sum, the biggest value then, which make the smallest number possible, So k minus, we said that's going to be what? K minus alpha plus 1, alpha minus 1. That's the smallest value. And you're going to run all the way up to the biggest value. So the biggest value for this guy here is when n is the smallest. You know that's when n is 1. K minus 1, alpha minus 1. And you're getting all the values in between. So the only thing to do to make this prettier is clean this guy up. So you know this is k minus k, it's going to be 0. Minus negative alpha, it's going to be positive alpha. Positive 1, take its negative, it's going to be negative 1. So really, this is going to become alpha minus 1, choose alpha minus 1, summed all the way up to k minus 1. But what we just argued is this is a nice way of literally counting just k choose alpha, right? The number of ways of picking alpha guys from k. So this is k choose alpha. So if you sit back and think about it, they're just different ways of saying the same thing. Okay? Obviously, if you're in a hurry and you're working through this, knowing identities helps, right? Knowing how these things connect help. But I think it's always fun to just look at it, imagine different ways, and the more comfortable you become, right, the more easily you can visualize different ways of seeing the same thing. Okay? And I think it's a huge part of combinatorics and really mathematics in general. So anyway, hope this helps. If you guys have questions, please let us know.